just a part of the like electronic structure problem is a part of the bigger molecular problem where you have electrons and nuclei, and you just for a moment fix the nuclei and solve the electronic part. Now the problem that really we're dealing with is a many-body eigenvalue problem with parameters, and it's written right in the middle of the screen. It's like we have this electronic Hamiltonian and the wave function. So now the problem is difficult because we have many electrons in general with increase in size of the system. Problem grows exponentially in complexity if you don't do extra approximations. Now, the hope that quantum computers can help us one day for solving this problem more efficiently than the classical computers is based on this well, simple consideration that usually people do. It's for a many-body problem, we introduce some single particle basis. In chemistry, it's called molecular orbitals. And so essentially we could use some sort of a mean field approximation in order to generate single particle orbitals and then construct antisymmetric products, which are called Slater determinants. Now, the solution for the full problem could be written as a, well, I don't see my, kind of, don't see my pointer, but okay. The line which is there is for the wave function psi, we have a linear combination of Slater determinant as a solution, and Slater determinants could be written as a essentially kind of strings of zeros and ones, because zeros would correspond to unoccupied spin orbitals, and ones correspond to the occupied ones. And then if you have n electrons and some number of orbitals, then the number of these products scales exponentially, roughly. So this is a difficult problem to solve. And then on the other hand, with the quantum computers, what we have qubits, and there are two-level systems that we can control. So there is a nice mapping, which we'll talk a little bit later and more in details. But for the states, it's a very simple mapping between essentially products that are antisymmetrized products of spin orbitals, Slater determinants, and products of the qubit states. You could think of them up and down, and zeros and ones map to up and down qubit orientations. That's one way to think about it. Or you could even just simply zeros and ones map to levels of the qubits, essentially. Now, with the power of entanglement, which you probably heard about, it's essentially the case when you have multiple qubits and you can control the superpositions of these multiple qubit states. Here it's like in coefficients alpha, beta, gamma, delta. This 2-qubit example where you can essentially with n qubits encode 2 to the n complex numbers that are in the amplitudes. And that way you could see how you could potentially, if somebody gives you the solution of the problem, you could write it down on a quantum computer as a superposition of the qubit states. But one kind of needs to realize that this is all great, but this is just essentially the quantum computer being a exponentially large piece of paper where you can down the solution if somebody gives you the solution. Now, the solution needs to be obtained, and that's where we come to quantum algorithms, essentially. That we need somehow to generate the solution, not just to write it down. And when it comes to quantum algorithms, they are, well, in the current stage, they are all, you probably heard about some sort of, we're in a noisy intermediate scale quantum device era where the errors that occur in the quantum computers, they are not corrected. And the typical algorithms that people use is a variational quantum Eigensolver algorithm that is based on essentially constructing some, with unitary transformation, some states, And then using those states, we measure the Hamiltonian and then pass this expectation value to the classical computer in order for the classical computer to suggest a new, for a minimization process, suggest a new trial function. And then the new trial function is constructed in a circuit and then measured again, and so on and so forth. So this is this kind of the idea of the variational algorithms that people have been playing these days, because the idea is that the circuits are relatively short, and then we need to do the measurement and get the results sooner than later. Now, there are quite a few methods that been developed how to construct unitary transformations that will be compact and generate the solutions for this eigenvalue problem relatively quickly and relatively accurately. These are a list of references. I want to say that one of the first algorithms that my group developed was a qubit couple cluster theory, and it's a first adaptive algorithm suggested. Then there was more development related to adaptive algorithms that trying to find how to build this unitary on the fly based on the energies expressions that one gets from the intermediate sort of measurements, right? And recently we had a review paper here that summarizes many constructions in this variational quantum Eigensolver technique. You could take a look and investigate more. Now, another problem with this approach is usually the measurement, because it turns out that measurements are not easy to do, simply because we cannot simply measure any operator in spite of what we teach in quantum mechanics for undergraduate students. If someone has a complicated operator, it's not so simple to measure it. So what needs to be done is, or what are we restricted with on a quantum computer, it's essentially Stern-Gerlach experiment. We can only measure polarization of qubits along the z-axis, and therefore, if you have a complex operator, then there's an extra unitary rotations that you need to do in order to get the expectation value of that more complex operator. So the various measurement techniques discussed in this recent review we put. It's very recent, so take a look if you're interested in the measurement algorithms, say in the variational quantum Eigensolver. But why I'm going relatively quickly over this variational part is simply because it has one big issue that cannot be resolved within this framework, and that the biggest issue of this framework is sort of the accumulation of errors. So now, if we are very smart about constructing the unitary transformations and even about the measurement, so then our error with the number of operations that we use to construct the unitaries will go down, and so we are getting closer and closer to our eigenvalues and eigenstates, right? But then, because we don't correct the error, the error will start exponentially, essentially taking back all the advantages that we acquire by doing all these smart quantum operations. And unless errors are corrected, there's not going to be any advantage, especially considering that in quantum physics or quantum chemistry in particular, people are interested in scalable methods, meaning that if you have small molecules, that's great. You can solve for the spectrum, right? But then if you want to enlarge the molecule, you ideally want your method to not grow computational cost exponentially, but grow ideally linearly, right? And that is not possible because with the bigger molecule, you will need more operations, and eventually you will get to this point where errors start accumulating, and essentially your quantum advantage will disappear, and soon the method will start producing the garbage essentially. Now, this is all a relatively long way to say that we need error correction, or we need to develop fault-tolerant algorithms, the algorithms that are okay with errors, because there is a extra part that corrects those errors, right? So those called fault-tolerant algorithm. Okay, and then one of the first and the most well-known algorithm that is considered like only applicable, kind of only possible when you can correct errors, because the circuits there, the unitary transformations are relatively long, is quantum phase estimation. And you could read about that in many places, but most of the places explain this algorithm in a very complicated way, which is very kind of natural for physicists, I guess, and chemists. So what in reality, the simple picture of what quantum phase estimation is the following few steps. Imagine if we are interested in my cursor again disappeared, but if we have an eigenvalue problem, phi n's are eigenstates, and we can construct the initial state psi that is always going to be a linear combination of eigenstates of our problem, because the Hamiltonian has a complete set of eigenstates, right? Then we can construct such a function as it's called autocorrelation function, and the function is inner product of time evolved initial state with the initial state, right? So it's a psi exponent of minus iht psi. And then we do Fourier transformation of that. You could convince yourself with a few lines of algebra that you're going to get a spectrum. And that's what is happening in quantum phase estimation. Quantum computer, you get this spectrum by doing the final measurement. And you essentially collapse to the state of interest if it has large amplitude in the initial state, right? So because of that, the two main questions here is, how do we build initial state with non-negligible, say, overlap between your state and the state of interest? And then the second part, which I skimmed through, but it's important, is how do we really construct this unitary propagator? Because the unitary propagator, it's not like somebody gives you complicated operator again, and it's easy to exponentiate it. Exponentiation, like if we go back to just elementary linear algebra, if somebody wants to exponentiate the matrix, even Hermitian one, you usually need to diagonalize, and then it's easy, right? But if we could diagonalize the Hamiltonian, then there would be no problem of essentially doing any of that, because we would after diagonalization get the spectrum, and the whole point of doing all this is to get the spectrum. So these two questions I will address further in this lecture, because the current, I guess, idea in the field is that the error correction will appear, and without it there will be no quantum advantage. And with the error correction, there is no maybe big value in doing the variational quantum Eigensolver solution, but people will use quantum phase estimation. And one of the actually historic fact, it's the creators of variational quantum Eigensolver, they initially come up with as an initial state preparation for quantum phase estimation. But then later, people liked it so much that they decided to, well, try to use it on its own. And we sort of, those who know the field kind of understand where it led. And now variational quantum Eigensolver is one of the most popular algorithm, but I don't think the future will be in developing that algorithm further. It's more like using it for maybe preparation of initial state. With that, let's first consider initial state problem. And the initial state problem is effectively the question: is overlap that of the state that you have with the state of the eigenstate of the Hamiltonian is good enough or not? And there was a recent paper by Garnet Chan and co-workers. There's a reference here. And so there was a reasonable skepticism about whether quantum computing could bring value, because what if most of the systems that people are interested in, industrially relevant system, they fall into two categories. The one that where you have with the classical methods, good good ways, approximate ways of calculating both energy and state. And those easy systems, they don't really need multi-billion-dollar quantum computers to be solved, right? And then there could be a second type of the systems where they're hard. Classical methods fail to predict the energy, but also they are, like all the classical methods, will be very for them will be difficult to prepare initial state in order for quantum phase estimation to start. And there will be nothing in the middle, or nothing important in the middle, so then quantum computers will not be useful. So that's kind of the one of the skepticisms about the quantum computers, and it really brings the question how good overlap one can guarantee. And it turns out that there is a work by Eckert, 1930, long ago. It's like almost more than a century ago, and it's a really undergraduate exercise in just a variational principle you could think of, that tells us that we could do the lower bound on the, let's say we're interested in the overlap ground state P0, and it turns out with a few inequalities one can start with the expectation value of the Hamiltonian with this phi as an initial state that you prepare, right? It will be a linear combination of eigenenergies with overlaps. And then if you substitute all the excited state energy EIs by just a first excited state E1, that just increases, or sorry, decreases the value of the sum. Then you could rearrange stuff so that and complete the sum over PIs to 1 minus P0, right? Then you could express the P0, which is a kind of overlap for the ground state between the ground eigenstate and phi. Then you could show that P0 is always more than this ratio. And what this graphically, it's easy to understand. What this means is the numerator is actually distance between the expectation value of your Hamiltonian on the approximate state and the first excited state. And the denominator is the difference between, essentially a gap between the ground and first excited state. Okay, so the simple truth is that if your expectation value of energy for the approximate state is at least in the lower half of the gap, then you're good, because the ground, if you are looking for the ground state, then the P0 will be more than 50% in this case. And if you look at the usual energy accuracy that people want from the calculations, it's a chemical accuracy, which is 0.04 electron volt. And if we look at some of the compounds that people are interested, like light organic emitting diodes, visible light gap is 1.8 eV. So getting into the 0.9 eV to get the good overlap is not that hard. Considering this, it's much harder to get chemical accuracy, because the energy accuracy that you need to get is much higher. But it turns out that not all systems are like these visible light gap systems. And there are some difficult systems in chemistry, especially when we start breaking some bonds, like take a simple molecule, water, right? If you start stretching the two hydrogens from oxygen at the same time, then it turns out that some of the methods that well, people use, like Hartree-Fock or beyond Hartree-Fock even, what they will be generating is some approximate states that are outside of the gap, right? And what this means is that the Eckert bound will be completely useless. It will be showing that P0 is more than some negative number, because then if your expectation value outside of the gap, the numerator will be negative, right? And so that's a problem. So what we did in the work that is cited at the bottom is we decided to really extend the Eckert bound and construct something that will be always accurate and potentially converge to the exact lower bound or exact overlap if you insist really. So essentially we want lower bounds and upper bounds, but I will consider lower bounds on this slide just for concreteness, right? And the way we can do this by creating instead of just the expectation value of the Hamiltonian, we take the so-called indicator function of the Hamiltonian, right? So what is indicator function is a function on the right side. It's the function where we have value for the value of energy, which is, let's say, ground state, but it could be any other state. Its function is 1, and for the other states, function is 0, right? So if we put, instead of energy, the Hamiltonian into this function, then it will produce, well, according to this simple equalities, it will produce the overlap exactly, right? Now the problem, of course, this function is too complicated to implement in terms of how do you really write this function of the Hamiltonian, right? So you could write polynomial approximation for it, but the exact function will be difficult to do. And so what we come up with is the algorithm which uses a polynomial approximation, but there is a twist. So normal polynomial approximation, if you do Chebyshev, for example, or some other, what it will do, it will produce approximation for this expectation value of indicator function. We don't need approximation. We want upper and lower bounds, right? So therefore, we specifically approximate in a way that will generate, in this case, lower bound. So we maximize the value of the expectation value with respect to all polynomials that are all below the indicator function, right? So we're coming from below and we're maximizing as much as possible, right? So that will allow us to create a lower bound. So it turns out that this problem is just a problem of adjusting the coefficients of the polynomial if you know relatively well where the spectrum is, because instead of manipulating with functions of a Hamiltonian, you can manipulate with a function of energy, right? And as shown in the lower left side, you just adjust the polynomial. And also this polynomial will be state specific. So for state phi, there will be polynomial which approximate indicator function the best from below. And so then if spectrum of H is given, then it's really a linear programming problem, which guarantees global minimum or maximum, right? So it's very easy. But of course, there's a chicken and egg problem because we don't have a spectrum of the Hamiltonian. So what do we do then? Well, in real systems, we just need to know upper bound and lower bounds on energies in order to implement this. And there's nice work by Eli Pollack and Rocco Martinazzo recently about finding lower bounds for the eigenstates. The upper bounds, they're naturally coming from variational principles, so one can use classical variational approaches to get some idea where your energies are, and then use our technique in order to estimate for a particular approximate state what is the lower bound for the overlap. Now, these are some results on lower and upper bound for small molecules, but they are actually quite hard in terms of getting well, here what we have is on the left, on the y-axis is always overlap. The blue lines are exact overlap. The curves correspond to lower and upper bounds. Whether we have exact eigenvalues or we have approximate eigenvalues, you could see we can converge, and the way we do the convergence is we increase the polynomial degree. So essentially, the higher the polynomial degree, the easier it is to approach the exact value. But we always can say what is the upper bound and what's the lower bound. Okay, so now what is this good for? If we have approximate wave function for classical method, you can evaluate Hamiltonian moments with it, with some knowledge of spectral bounds. And upper bounds that we are getting, they are equivalent to no-go statements, meaning that if your upper bound is less than like 10 to the minus 3, then it's probably you better improve your estimate for the wave function. And the lower bounds success guarantees. Essentially, if you lower bound is more than say 20%, then 1 out of 5 times you will get the state that you're interested in. So and accuracy can be systematically improved. These are optimal upper and lower bounds essentially. So details you could look up in the mentioned reference. Now let's get to the Hamiltonian encoding problem. And as I said, it's not that easy to exponentiate the operator whose eigenvalues you don't know. And just to establish some notation, we will deal with electronic Hamiltonians, and in the second quantized form, fermionic operators of creation and annihilation. There are some coefficients h and g. They are tensors of 1 and 2 electron integrals. Those obtained on a classical computer, so we can set up for any molecule essentially this type of Hamiltonians. And then, as I said, we can easily map fermions to qubits using various fermion qubit mapping. So Jordan Wigner, it's almost like 100 years already, established the mapping that works to this day. It's quite nice, simple. X, Y, Z are the products, and then we can establish the connection between every creation and annihilation operator to essentially few products of X, Y, and Z's. And then by doing this, we create isospectral Hamiltonian HQ that has exactly the same spectrum, the electronic one, but now written in a linear combination of Pauli products, large P's. Okay. Now, the first way to approach the problem of exponentiation of the Hamiltonian is something that you probably have seen in a few places, so-called Trotter approximation. We break down the Hamiltonian into parts that we can exponentiate. And what this means is we just can simply analyze these Hamiltonians, and the Hamiltonians that we can diagonalize, well, they are in this essentially form that we have unitary transformations and diagonal operators. Now, what diagonal operators can we use in this context? It depends whether you wanna work in a qubit space. Then in the qubit space, you have a option that in computational basis, the diagonal set of operators that are produce diagonal matrices. They are just simply polynomial of sigma z, or z in short, Pauli operators, right? And then alternative to that is to work in the fermionic space, and then I'll figure out what kind of operators you can diagonalize, and then go to the qubit space. So as a reference for the fermionic space, the diagonal operators would be occupation numbers, because they map into the z operators when we do qubit fermionic mapping. Now, the next big question is, what Hamiltonians can we diagonalize? Can we be into these diagonal forms? What are the HNs we can deal with? And that's the first problem. So let's consider it. Like in general, there are so-called fast-forwardable or exactly solvable with simple unitaries Hamiltonians, and some of them are quite well known. Let's say in the qubit space, we know that linear combination of all commuting Pauli products or anti-commuting Pauli products, they can be easily diagonalized, commuting ones with Clifford transformations and anti-commuting ones. I can show later how it's done, but both of these types turns out to be easily diagonalizable. There are more general combination of Pauli products that were found recently. They are combination of commuting and anti-commuting operators that can be still diagonalized. The archive reference is mentioned here. Now, in the fermionic space, if we look at the fermionic parts, the easy kind of intuition about the things we can diagonalize are those are Hamiltonian solvable using Hartree-Fock or Hartree-Fock-Bogolyubov method, right? And once you have this diagonalizable Hamiltonians, you need to find them in H in order to do diagonalization, essentially. Now, when we work with the, say, qubit first, and then we partition the Hamiltonian to the diagonalizable ones. So what we can do is, let's say I skip coefficients here. Typical example could be the Hamiltonian, which is a linear combination of these products. What could be used in order to find the, let's say, commuting parts is to use graph techniques, where we partition the graph that originates from just making every Pauli product as a node and connecting the nodes that are commuting, right? So commutativity is a transitive relation without, binary relation without transitivity. It's like one can say that commutativity is like friendship. If you have a friend and your friend has a friend, it's not necessarily that you are with a friend of your friend, right? So the same with the operators. If two operators commute and the second one commutes with the third, first and third not necessarily commuting. And that's what makes graphs perfect for expressing the commutativity. And then what we can do is to partition the graph into fully connected subgraphs. And that's a typical graph language problem, and it has solutions. In order to build a minimal number of such commuting parts, it turns out it's a very hard problem if you want to minimize the number of fully commuting parts. But there are some polynomial heuristics, and these are the works where we worked on or discussed those polynomial heuristics. It turns out that greedy heuristics work quite well for the Trotter error, and I'll tell you why in a moment. But turns out you don't need to partition the graph into minimal number of fully commuting subgraphs. You could do things in a greedy fashion, and it will be even better. Now, if we discuss the fermionic algebra, how it works, so we can look at the problem in the following way. So we look at the Hamiltonian and say, all right, could we partition the Hamiltonian into sort of fragments that can be solved exactly with a mean field approach. And simple solution to this problem, which many people in quantum chemistry at least know very well, it's one electron Hamiltonians, and they can be with the orbital rotations turned into just a linear combination of occupation numbers, right? So these are orbital rotations, and it's a kind of simple transformation. I can go into the details later, but all you need is to diagonalize the HPQ matrix to find this rotation, which is very nice. Now, but this nice example, unfortunately, doesn't answer the question, how do we do this for the Hamiltonian, which is generally 2 electron? It doesn't contain only 1 electron part. It has also 2 electron part. What do we do with 2 electron parts? Oh, it turns out that once you know the kind of the form of the solution, and it is unitary orbital transformations conjugating the occupation numbers, right? So then in order to make a 2 electron fragment, all you need is to switch 1 electron or linear combination of occupation numbers to quadratic form, right? And that's what we did. So if you take the quadratic occupation form and then do the orbital rotations, you will get the fragments that are looking like a normal 2 electron fragments, and you will not recognize looking at them that, oh, they are actually solvable exactly by Hartree-Fock method, because Hartree-Fock method finds these orbital rotations that bring things to the occupation number form, right? Now, if you have these 2 electron blocks, then you could simply make sure that the left-hand side of H equals to sum of HNs equal to the right-hand side. So it's just a fitting problem. You fit one operator to sum of others and adjust the unitaries and lambdas in these fragments to essentially do the partitioning. So that's the fermionic algebra case. And the nature of question one can ask, which fragments are better, qubit or fermionic? And in what sense better? Of course, well, in the sense of if we do fragmentation using one type, what sort of error does it introduce? Because as you could see, it's a Trotter approximation. It introduces the error when we switch from the exponential of the sum to the product of exponentials. And once want to minimize that error, one way to minimize that error is to by reducing the time step t, right? And but of course, then you would need to do more steps, right? So computationally, this is not as advantageous as figuring out a scheme which has smaller error with a fixed t. Okay, so how do we estimate error? So actually, it's quite recent work by Andrew Childs and coworkers. They found that if you take the norm of the difference between the two evolution operators, then you can upper bound it with the sum of norms of commutators. And it's not easy to sort of calculate the norms of commutators, because even if the operators that are involved in the commutators are diagonalizable, commutator of 2 diagonalizable operators not necessarily diagonalizable, right? So, and finding the spectral norm of it is not straightforward. Therefore, what we did in the work that is cited below, you could see the details, or we could discuss the details there. We found the upper bound for this upper bound, right? And it is our upper bound essentially based on one important quantity, and it's called spectral range, delta E's. So if for each fragment, you could find the minimum and the maximum eigenvalues, right? And find the difference, that's the delta E. And then you could show that the sum of these commutators, norms, it's actually less or equal than these two expressions. Now, the first part, the first product, is you could think of it as a total spectral range. So it's a sum over spectral ranges squared. So that's one component, and the second one we call entropic part, and we call it entropic because it is related to so-called informational entropy. So now, if you have a distribution of spectral ranges, right? So omegas right there is like a difference, ratio of one spectral range of the of particular fragment divided by sum over spectral ranges, and sum of omegas is 1, and all omegas are between 0 and 1. So nice. So they can be the entropy could be analyzed as an entropy of any distribution. It's like Shannon's formula with logarithm, and if you linearize it, take a Taylor series, then you get the expression that we obtained, the sum over squares of omegas. And why I'm going in all these details, because it turns out once you realize what are the sort of parts of this expression, you could optimize the error more efficiently. Because then you get an intuition that the smaller spread of eigenvalues will be better, right? So you would like fragments with a smaller spectral range. And also you realize that non-uniform distributions are better than uniform distributions. Why is that? Because we know the entropy is highest when the distribution is like the most democratic, the most uniform, right? And if you have distribution with just one big fragment and others small, then we have a small entropy, right? So that's good. And that brings us to the point that I was making earlier, that greedy algorithms, they generally tend to create first fragments bigger and the other fragments smaller. Here's the simple illustration. If you do with a greedy fashion, fill in the square with the circles, well, the first circle will be the biggest, and then smaller and smaller and smaller. Okay, so that's easy to understand. Now, let's see some results. If we look at some small molecules where we can calculate everything in order to analyze these methods. And on the left-hand side, we have this sum over norms of commutators. And the x-axis, we'll have like different methods. So qubit algebra in blue, non-greedy approach that tries to minimize the number of fragments. And dark blue, the light blue is greedy approach. So these are, as you can see, errors across the molecules. Greedy is better everywhere. And then the fermionic algebra, again, the non-greedy is red and greedy techniques is in orange. And again, you could see the same trend. Greedy is better by, well, the logic that I just described, right? But what is even better than greed in this case is, as you could see, fermionic algebras, they're usually better than qubit algebras in all cases. The conserving of molecular symmetries, that's what is happening when we do fermionic fragments, because fermionic fragments commute with the kind of natural symmetries like a number of electrons, spin, and so on, right? And why is it important? Because then if your fragments commuting with symmetries, you can reduce the space over which you consider spectral norms to the subspaces of relevant symmetries, right? And all of these methods of grouping are better than just simple Pauli product decomposition that was done before, I guess, our work, that Hamiltonian is considered just a simple linear combination of Paulis, and every fragment is considered to be a single Pauli product, right? So now, sounds like a success story, and now we know fermionics are better. But after this, we decided to see Okay, so Trotter error, we use the proxy, this spectral norm of commutators. Or what if we just simply look at the relation between this proxy, the upper bound for the error, which is the norm of commutators, and the actual error? Because what we can do, we can just simply substitute the unitary evolution by Trotter and calculate the difference in energies that we get, right? How good is the correlation between two errors? Here's the result. So there's a proxy on the y-axis and the actual error delta E on the x-axis, right? So as you could see, you don't need to be a professional statistician. There's almost no existing correlation, okay, between these two. And well, the reason for that is that looking at upper bound not necessarily give you a good sense of what the actual error is. Okay, so then we decided to go after actual error. How do we do that? What you can do is take a Trotter expression and write it as a single exponent, right? So you could do that. There is an expression for that. If you could write a single H effective generator, and then there is a so-called Baker-Campbell-Hausdorff formula for the expressing the H effective through the HNs, fragments of the H. So naturally, the first term is H itself, and then other terms in HF are you could think of them as perturbing terms, V1 and V2, which it's like commutators and double commutators and so on. So in order to understand or analyze how the different the spectrum will be from H and H effective, what one can use is perturbation theory. So you could take a perturbation theory up to the second order. It will contain two terms because V1 comes with delta t and V2 comes with delta t square. You need to be careful with the bookkeeping of the orders. And so for the second in delta t order, the energy correction will be expressed as we did at the bottom, right? So this can be calculated, and that's what we did. So of course we didn't have exact states. We calculated with approximate states, but in this work, relatively recent work, you could see more details. But the idea is that there is a almost perfect correlation between what the actual error is and what the perturbation theory estimate is. And then, so perturbation theory is the way to go. And if we now look at the best fermionic method versus best qubit method for using actual error, so then the picture is different. Qubit fragments are actually much better than fermionic ones, and that's the situation. And if you would like to analyze the Trotter error, the lessons here is you should not be using the upper bounds for the difference of norms of the propagators. You should use this perturbation theory for the eigenvalues, and generally qubit methods are better than fermionic ones. Now, Trotter error is still giving you roughly scaling with the total time of propagation as a square, right? And one can do better. That's post-Trotter methods these days. People consider a so-called linear combination of unitaries as a way to block encode the Hamiltonian. And I'm not going to go much into the details. Many of these things that I go maybe relatively quickly, you could check on my YouTube channel. I have lectures which go slower in each topic, and if you want to learn more, you could take a look at them. So just type my name in YouTube and you will see the lectures. All right, so but back to this post-Trotter methods, the idea is that with extra qubits, you could do some really interesting stuff. Like we know that in the normal circumstances, sum of unitaries is not a unitary. But if you add tensor product extra projectors, then turns out you can sum the unitaries. And this is the key to turn the linear combination of unitaries that you can always present your Hamiltonian as a Hermitian operator into one giant unitary where Hamiltonian is just a part. Okay, and this is the key to so-called qubitization method. And in the qubitization method, what it allows you to do is to construct instead of exponential function of the Hamiltonian, it allows you to construct exponential function of arc cosine of Hamiltonian. And this is still very useful because it is a unitary transformation, and you could again measure phase for these transformations. And the phase will be arc cosine of energy. So then you could just take a cosine of the phase and you get the energy back. Now, the nice thing about this approach is no Trotter-like error. There is no non-commutativity here. Everything, well, just there are no commutators involved. But of course, as a conservation of misery in life, we have another problem. And it turns out in order to do all this stuff, you need to normalize Hamiltonian by its one norm. Along the path of getting these expressions, the one norm will appear. And then in order to optimize the algorithms based on this linear combination of unitaries, what one needs is to reduce the cost that corresponds to one norm of the coefficients, right, of the linear combination of unitary decomposition. Because you can do decomposition many different ways, they will have different one norms. You want to pick the one that has a lower value. That's the game here. And in my research, so we decided to first see what's the absolute lowest one can get, right? Before we engage into the game of figuring out what unitaries to use, what's the absolute lowest one can get? And it turns out that you could show that if you're Hamiltonian, you write it as like a trivial part, just a shift, identity times S, plus some non-trivial decomposition. And you could show that, again, the spectral range, difference between the largest and lowest eigenvalues, will appear as a lower bound for the non-trivial part. And to show that is just a one-line proof using triangle inequality. We could go about through that if you want, but it's just at this point, just trust me that this works out. It gives us very convenient quantity to work with, well, spectral range, right? So if you have a Hamiltonian with a large difference between the largest eigenvalue and lowest eigenvalue, it will be difficult to present it as a low one norm unitary combination. Linear combination of unitaries, right? So there's a hard limit. And one way around, of course, is to change the Hamiltonian, right? So, but it sounds like it's a difficult thing to change the Hamiltonian until we realize that, okay, where do we live really in these problems? We start with the second quantized form, and that's a Fock space. And there is a saying that the Hilbert space is big, super big, right? But the Fock space is even bigger because it's a direct sum of Hilbert spaces. And here we develop so-called Bliss technique, block invariant symmetry shift, that take advantage of the fact that our Hamiltonian comes from Fock space, and it has this structure that, let's say, the number of electron is a good quantum number, right? So all the, like, we have blocks for the entire Hamiltonian, blocks of Hamiltonian corresponding to a particular number of electrons. And then we can realize, okay, well, if we, let's say, look at the water molecule, experimentalists may be interested in neutral, cation, anion. They're not interested in -5 water molecule, right? Because it's not physical, but it's still in this space, right? So we don't need it, but it is in part of the Hamiltonian. Now, what can we do then? We can change the Hamiltonian, because some of these strange forms of water, they may have energies which outside of the range that we or range of energies of the forms that we're interested in, right? So on this picture, you could see E max and E mean may correspond to some values that are larger than E max and mean of the, like, a blue zone, which is the number of electrons that we're interested in. Right? So we could change the spectrum, we could change the Hamiltonian for those forms that we're not interested in. Nature will question why not to work with projectors. Projectors are complicated operators, unfortunately. Instead, we create so-called killer operators. Killer operators are the operators that kill the state of the right symmetry. You may wonder, why do we do that? It allows us to modify the Hamiltonian, right? So with these killer operators, that modification will not change the action of the Hamiltonian on the states of the right number of electrons, but it will change the action of the Hamiltonian to their own number of electrons, right? So that's the idea. And this is how we build these killers in a very simple manner. We have some free operator multiplied by number of electron operator minus the constant corresponding to the right state, right number of electrons, or right meaning that what we're interested in. And then we can optimize this free operator O in order to minimize, well, in this case, we minimize one norm in terms of linear combination of Paulis. Why? Because Paulis are unitary, and because this optimization turns out to be linear programming. So we can find global minimum, right? So it's advantageous. All right, so I'm kind of running out of time. This all works very nicely. These killers are as good as projectors, pretty much. You could see the details in our works. They for the small molecules where we can do projectors and killers, we are within 1.5% of the spectral range, and we could do even more complicated unitaries, not only Paulis, by grouping using the fragments that we used in Trotter, but here we can use the same sort of fragments. The only thing is that we need to switch between the number of electron operators for each spin orbits to reflections, because we want to build unitaries, and it's very easy to do. So then we have multiple works these days on what are the techniques, what's the most general form of the fragmentation to unitaries, and what are their characteristics. This grouping always helps. The usual picture is Pauli decomposition gives you largest norm, grouping lowers it, and lowest is, of course, spectral range. And we have quite a few results. The main important point is this killer operator changes spectral range of the Hamiltonian, because we change the spectrum in the wrong side of wrong parts of the kind of number of electron sections, right? And then that allows us to really reduce one norm with h minus k, like factor of 3 roughly in the case of small molecules. In the case of big molecules that are more of industrial interest, we could get factor of 10 compared to naive Pauli decomposition of the Hamiltonian. But there is still room for improvement if you look at the spectral ranges. And what concern we had when we were calculating this is whether we can beat classical methods like DMRG for these industrially relevant systems, and in terms of time to the solution. And if you look at the works that blue and red reference, so there are some reasons for the optimism. There are some compounds that DMRG is still winning, but there are some that are hard for DMRG, and quantum can deliver some advantage. And yet another kind of very simple point here is that we looked at some small systems and tried to figure out whether there is a correlation between difficulties that appear when we break bonds, right? So this hump here in the lower plot corresponds to the energy error. And that's the regions which are hard for classical methods. And we look at the quantum hardness. Let's say one norm is a quantum hardness. Across this bond dissociation, we saw that actually quantum hardness is not correlated with the classical hardness, which is good because then we know that for systems that are classically hard, quantum algorithms may have advantage for the situations where the systems are especially hard for classical. And this I will skip. Now let me summarize. We developed some methods for initial state preparation since it's a first step. And we would like to certify the overlap. Now we can do it by just classical calculation of moments of the Hamiltonian. In Trotter approximation, which is a way to encode the Hamiltonian, we built quite a few fragmentation schemes and now know how to analyze Trotter error very well for them. Now in the post-Trotter methods, it's mostly about one norm, but fragmentation methods help. And we also know now how to maybe modify the Hamiltonian to reduce the spectral range, since that will regulate the success of the decomposition methods. This is acknowledgement to the group who worked on these problems, and funding agencies. And of course, thank you all for your attention. And I'm happy to take any questions.
Okay, thank you very much, Prof. Artur, for your interesting and enlightening presentation today. And today's talks give us valuable insights on how partitioning the electronic Hamiltonian into simpler fragments can improve the efficiency of the quantum chemistry algorithm like VKA or KPA. And to all the participants, we now have 30 minutes for our Q&A sessions. And if you have questions, you can either post your question in the Zoom chat or raise your hand if you would like to ask your question directly to the speakers. So I see we have a question in the Zoom chat. Let me write it out. The first question is come from Kaisnan Ledito. So he is about the lower bounds. Do you need to know the spectral graph in order to find the lower bound?
Okay, so lower bound, right. So I guess the question is related to the estimating the lower bound of the overlap, and spectral gap is the difference between the ground and first excited state. In the Eckert expression, which just uses the first moment, yes, you need no spectral gap. You could estimate it, but yeah, the lower bound requires no spectral gap. Now, for everything we develop, we kind of do not require knowledge of exact eigenvalues. You can use approximate bounds for the energies. ground and first excited and so on.
Okay, thank you for the answer. Is there any comment from Kaisnan Ledito? Is okay the answer? I think we can go to the next question also. I think because he asked about the lower bound, and then I will follow up the next question from Kaisnan Ledito also. Is your lower bound theorems only guarantee if the block encoding Hamiltonian is a sum of Paulis? If so, can one generalize it to the other classes of Hermitian operator?
Okay, is your lower bound theorem only guaranteed if the block? No, it's my lower bound theorem is simple and great because it does not assume anything about unitaries, right? So they can be Paulis, they can be more complicated. By the way, I can show how to build the unitaries that make the lower bound equal to the one norm. So there's a way to construct such unitaries. They're not practical, but such unitaries can be constructed and they will saturate lower bound. But lower bound with the spectral range is independent of what unitaries you use.
Yeah, thank you. And also, is there any question from others? Rafika, there is question from Rafika. Can this method, I think the Trotter error, to reduce the cost of simulation on classical computer when simulating complex quantums, because you saw the case of water molecule and also NH3 quantum computing problem, especially if we apply for the noisy environmental problem.
Right. So the issue, I guess, there in the classical methods for using Trotter approximation, if you can use classical methods for Trotter, then reducing Trotter error, of course, will help classical methods as well. The problem of classical methods is how to, like, once you, say, apply one fragment exponential of one fragment, then switching to another fragment and applying and keeping all this, you're gonna get the superposition of states after application of one state and switching to the framework of another. And that superposition of state would essentially, yeah, it needs to be somehow contracted, maybe using tensor network or using some techniques, but you cannot keep everything in like memory because then it becomes complicated. Like this Hilbert space is just exponentially large and it will kill you. You won't be able to do the Trotter simulations unless you find a way to approximate at every step. Yeah, that's but the person who asked the question, I guess, maybe knows more about the classical Trotter approximation, and my simple answer would be yes, you could use this analysis of Trotter error. Classical or quantum doesn't matter.
Okay, thank you, Prof. Artur. There is a comment from Kaisnan also. So the great thanks for your answers. And one more questions. Does pre-symmetry can mean that the Hamiltonian simulation is easy to classically simulate as well?
In principle, yes, because when you preserve symmetries, you're always in the subspace, which can be exponentially still large, but it's smaller than the full space, right? So let's say you have some exponential Hilbert space, exponential in terms of the number of qubits, let's say, and then if you impose symmetry constraints to fragments, so then you can guarantee that the Trotter, say, evolution will stay within and if you start with a state that is only in a particular symmetry subspace, it will stay in that symmetry subspace, right? So that for classical simulation, that would be beneficial as well. So.
Okay, thank you, Prof. Artur. Is there any question from other audience? If no, maybe I would like to ask the question about the your data, the trotter error with respect to the molecule, and is in the y-axis. In the y-axis, it's represent the sum of double commutator norm, right? And in this case, is the unit is dimensionless, right?
Well, it's a norm of commutators, right? So then you also have right. So the okay, that's dimension is right because you have t squared times the norm of the commutators, right? So commutators quadratic, and then you have a t squared as well, right? So that's
okay.
That's a correct. T squared is skip because it's this. It's a time step that is the same for everything.
So it means that it has unit that consistent with the energy square.
Right.
Okay. And for the data, for especially for the NH3 molecules, you see that the error is very big if you compare with the linear molecule. So in this case, for the complex molecules, you mentioned that you need to like preserving symmetry, but for the more complex molecule, for example, if you would like to design the protein and so on and so forth, and do you have any further suggestion to improve these strategies?
Right. So for the larger molecules, it seems to me that for the probably the future that we will have in 5-10 years, it's quantum computing will not be reasonable to use to large systems where the size is big, but the complexity is maybe within a certain subspace, right? So what I mean is that proteins, they're probably the metal protein part, that metal complexes that are making the calculations hard, and the rest of the protein can be treated by classical methods very well. So one would envision doing some sort of a downfolding or doing some sort of a treatment where it's a hybrid treatment. The environment is treated at a lower level, while the core that contains a lot of entanglement and needs to be treated accurately could be treated with the quantum methods. But for that, in order to implement this program, one would need to do the Hamiltonian kind of production with these techniques where you already treated the environment and now can focus on the system.
Yeah, thank you. And one more follow-up question. So if we're dealing with the QPA, quantum-based approximation, and then the problem is very big circuit, right? Other than to set up the initial state, we have very big circuit deep for these cases. So if we're dealing, for example, protein folding and so on and so forth, in this case, is in this case, I mean, just a quantum algorithm, full quantum algorithm is possible. So I mean that because of the limitation of the full quantum algorithm, so VKA is exists in here.
The question is whether it's possible to use full quantum algorithm for what problem? For
Yes,
electronic.
for the more complex system. Because of if we're dealing with the full quantum algorithm like VA, quantum-based approximations, we will have very deep circuit, right?
Right.
So in this current situations, the quantum computing is still have many noise. So the coherent time is very limited for these cases. So I mean that if we just try to improve the
But
Hamiltonian partitioning, so it means that it does not work.
yeah, maybe it wasn't clear from the beginning. I said quantum phase estimation, because the circuit is long, it's not possible unless you know how to correct errors, right? So
Oh, I see.
if errors are happening, you are correcting them, and
Okay.
that's the assumption. If that is not true, then you cannot run quantum phase estimation. That's why quantum phase estimation is not well, maybe well, people don't run quantum phase estimation on IBM machines that we have right now, because well, simply you will be able to do it maybe on 1 or 2 qubits, but that's it, because you will quickly run out of as you said, coherence time. All these errors will accumulate. So that's why people do VQE, because VQE requires shorter circuits, but it will also come to the end, because this circuit, like, you cannot use VQE, and as I said, when the system becomes larger, then you will eventually run out of steam because of the error accumulation, right?
Thank you, Prof. Artur. So in this case, if we would like to use quantum phase estimations, we need to also accommodate the quantum error correction code inside, right? Without that, it's not possible to to use quantum phase estimation, right?
Well, it's coming, right? So that Google announced Willow chip that actually already demonstrated some error correction, and so the error correction is coming. It's just gonna be slower process because we need to wait for hardware. Right?
Thank you, Prof. Artur.
But that's the future.
Okay, thank you. There is a question from student. Can we eventually avoid totalization in all kind of Hamiltonian simulation?
Okay, the answer is yes. The LCU and qubitization is the way to avoid trotterization or approximation related to the trotter. Now, the answer is yes, with some extra reading if you want not just eigenvalue problem, but quantum simulations in the sense that kind of time dynamics, right? Because qubitization gives you this arc cosine of Hamiltonian, and there, but you need exponential of the Hamiltonian. So trotter is very natural for that. I didn't talk about that because that was not focus of my talk. It's not an eigenvalue problem. It's just kind of doing the time dynamics, right? So because sometimes people say Hamiltonian simulation, what they mean is eigenvalue problem, and sometimes they mean simulation of time dynamics, right? So for time dynamics, qubitization also could be used, but there are some other approximations involved because we are getting arc cosine instead of the normal Hamiltonian exponent. But avoiding trotterization is possible.
Okay, thank you, Prof. Artur. Is there any question from audience? Okay. No question, I think. So I think if there is no question, we can close for this online colloquium today. So thank you for your amazing presentation, Prof. Artur. And it has been truly insightful colloquium once again. Thank you so much for sharing your time with us today. We do really appreciate your time. And let's officially close our colloquium today. We have come to the end of today's BRIN Quantum Physics Colloquium. And thanks to all the participants for joining us. We truly appreciate your time and interest. And we look forward to seeing you again at our next BRIN Quantum Physics Colloquium. Have a great day, everyone. Thank you, Prof. Artur.